So the first sort of real physics topic we'll discuss is linear kinematics. Kinematics is the study of motion. Linear means in a straight line, and one just means this is slide one. And so what we're going to talk about first is position, time, and velocity, and a few other things. So we're going to define position, displacement, and distance traveled for an object moving in a straight line. So let's say we have a car and its initial position relative to some coordinate system is x1. I'm going to draw a picture of this for you in a minute. Later, after the car is moved, it's at position x2. The displacement then is the change in position of the car. Displacement is a vector version of that, and so it includes the direction. In a straight line, you can just either have the forward direction, which we'll call positive. Let's say instead of forward, we'll call it to the right. And then the negative direction, which would be to the left. So if the car is initially at position x1 equals 3 meters, and later it's at position x2 equals 8 meters, then its displacement is delta x. That delta we use as a change in it. So delta x is x2 minus x1. It is 8 meters minus 3 meters, or 5 meters. Its displacement is 5 meters in the positive x direction. Its distance traveled is also 5 meters, but the distance traveled is just does not necessarily include direction. So if this car had moved 5 meters to the left, its displacement would be minus 5, but its distance traveled would still be 5. And so let me draw a picture of this. So I have a car, and so let me draw, I'll draw it this way. So this is my x-axis, and I have a car over here, right? This looks surprisingly like my car. And its position is x1, and we said that's 3 meters relative to this coordinate system. Later on, it's at position x2. Which is 8 meters. And so if we want to know its change in position, delta x is x2 minus x1, which is 8 meters minus 3 meters, or is 5 meters. Now you can play around with this and say, well, what if this was x1 and it was going this way? Then the next one would be 8 meters, x2 would be 3 meters, and it was 3 meters minus 8 meters, which would be minus 5 meters. Right? And so my displacement would be minus 5. But in either case, the distance traveled, let me see if I can spell that word right. There's 2 L's there. It's 5 meters. It's just the absolute value of the distance traveled. Sometimes we'll use a D here. I know displacement and distance start with the same letter, but sometimes we'll call this quantity d for the change in position, distance traveled. Okay, and so let's go to the next slide here. And so now I said instead, let's erase this for a second and redraw it slightly differently. This time we're going to say it went backwards. It started at position 3 meters, and it ended up at position minus 8 meters. And so I'm going to come back and draw this again. So here's my car again, and this time I'm going to say it's at position x1. I conveniently drew my car so it looks like it could be going in either direction, equals 3 meters. And here it is later, it's moved in the negative direction. Now it's at x2, it's minus 8 meters, right? So my 0 on my number line is somewhere in here, right? This is my x direction. Right. And so now I can say delta x, which is exactly what it was before. It's x2 minus x1. It's minus 8 meters minus 3 meters. which is minus 11 meters. And so that's how far the car traveled during this little jaunt. Okay. So now we're going to start talking about velocity. And the way we talk about velocity is we start including time in these discussions. And so if the car was initially at position x1, just like we said earlier on the first slide, at time t1 it's 2 seconds. And then, so you look at your watch and your watch says 2 seconds, whatever that means, right? And then at a later time, its position is x equals 2 and the time is 5 seconds. Then we can say, just like we did before, we can say, well, the displacement is x2 minus x1, which is 8 meters, minus 3 meters, which is 5 meters. But now we also have a time difference. It took it 3 seconds to make that change. And so this allows us to calculate what's called an average velocity. We define the average velocity. That is to say, the definition of the average velocity is the change in an object's position divided by the change in time. So it's the displacement divided by the time change, right? How long it took to travel that distance. During this time period, then its average velocity was v average, which is delta x over delta t, is x2 minus x1 over t2 minus t1. This is 8 meters minus 3 meters over 5 seconds minus 2 seconds, or 5 meters over 3 seconds, or 1.67 meters per second. Notice when we did this, we calculated a velocity, and we got the units we expected to get. We got meters over seconds. We got length over time, right? That's what velocities are. So the average velocity over this time period is 1.67 meters per second. It's a positive number because the car was moving to the right. The velocity is in the positive x direction from our first picture. Notice, by the way, this is just really, it's important to say this is an average velocity. All we know is that the car was at position x1 equals 3 meters, and then 3 seconds after that it was position x2 equals 8 meters. We don't know that it just smoothly drove to that, or if it went to Mars and back and landed in that second spot the second time at x2 equals 8 meters, at t equals 5 seconds. And so all we know with it is it traveled that distance in that time, or it changed position by that amount in that time. We don't know what happens in between, and so we call it an average velocity. An average velocity is just whatever its change of position is divided by that time period. So now I can do the same thing for the second case. I can say, well, look, suppose it was at x1 equals 3 meters at time t1, again, is 2 seconds. And the later it's at x2 equals minus 8 meters. This is the second example we were doing a few minutes ago. And the time then was also t equals 5 seconds. And so instead of going forward to plus 8 meters, it went backwards to minus 8 meters. By the way, I'm just making these numbers up. There's nothing special about them. Its displacement then is now negative 11 meters. We already figured that out in the second slide we looked at. Once again, it's the time change during which it made that transition is 3 seconds, 5 seconds minus 2 seconds. Again, we can calculate using the same equations. The average velocity is the change in position over the change in time, and we get minus 3.67 seconds. Notice this velocity is negative because the car is traveling in the negative direction, the same way as the displacement is negative because the car moved in the negative direction. The average velocity of this car over the time period is then minus 3.67 meters per second. Since minus 3.67 is a negative number, the average velocity is in the negative x direction. So we're going to take a look at this from a graphical standpoint. So let's go on to the next slide. And you can see here, hang with me on this. Hopefully it doesn't look too complicated. All you really need to notice here first is that this is a position graph. The x is the position, and that's the vertical axis. You're probably used to seeing, or maybe the last time you took a math class, you saw a y versus x plot. Well, you can plot anything versus anything, and here we're plotting the x, its position on the vertical axis, and time on the horizontal axis. And so if we were to just talk about this car, we'd say, well, x1 was 3 meters, and x2 is 8 meters, at least in our first example, and t1 was 2 seconds, and t2 was 5 seconds, and then we can just draw a straight line through that, right? And that would be sort of an indicator of the motion of the car somehow, right? If it was moving in a smooth way, not like the case where it was going to Mars and back. And so we can see that the change in position, delta x, is just the vertical change in the position of the car during the time that the horizontal change takes place. The horizontal change is just my time difference. So this is my change in position, this is my change in time. And if you remember anything about graphs, you know that if you have a line, the slope of that line is the rise over the run, right? And so it turns out that in a velocity versus time graph, the slope, in a position versus time graph, the slope is the velocity. And so we can talk about these a little bit. Let's go to the next slide. So, like I said, a position versus time graph, the velocity is the slope. Since the line is straight everywhere and not curved, the slope is the same everywhere. If I just page back up here, anytime you have a line that's straight, you might remember from your math class, the slope is the same everywhere on this line. If I do a rise over run up here, I'll get the same thing as I get it here. Or if I take the lowest point here and I do a rise over run with the highest point, that slope isn't changing anywhere on that line. You can see it by looking at it, and so the rise over the run is going to be the same. And so that means the speed of the car is constant. In a position versus time graph, if the line is straight, not horizontal, but straight, not curved, then the speed is constant. So we can look at these pictures and say, well, what can we say about these 3 different cars? One has a position versus time graph that looks like this, a C, one looks like B, and one looks like A, right? Hopefully you can see that A has a larger slope and therefore a larger velocity, right? B has a smaller slope and therefore a smaller velocity, and C has a smaller still slope, and so again a smaller velocity. And so let me just draw a couple of these on a graph, right? If I look at if I draw a position versus time graph, right, and so here's my x and here's my t, and I just draw a line like this. This was my A, say. Notice, so let's say this is my B and this is my C, say like this. And let's say I pick 2 times, right? Here's T1, and let me pick one over here, T2. I want it to be on all the graphs, right? So if I look at what's happening with this is my A, this is my B, and this is my C. I don't want to get too complicated here, but I'm trying to draw a straight line up. I'm not doing a very good job of that. But notice that between time T1 and T2, car A travels this distance, delta x. We'll call it delta XA, right? Between times T1 and T2, car B travels this distance. This distance that car B traveled is smaller than the distance that A traveled, and so on. Delta XC looks like this. Looks like that. And so the shallower the slope, the flatter the slope, the slower the average velocity of the car. So in this case, A was going the fastest, C was going the slowest. Right? And since the lines were straight and not curved, all the cars had the same, or were traveling at constant speeds, constant velocities. So tell me what this car is doing. Can you figure that out? Notice that if I start here and I go over to here, what is my x2 versus my x1? They're the same, right? This is a stationary car. Oops. So the speed of that car is 0. Similarly, I can ask you, if the line is sloping downward, what's this car doing? Right. Notice in this case that x2 is less than x1, and so when I take x2 minus x1, I'm going to get a negative number. If this is 3 and this is 8, delta x is 3 meters minus 8 meters would be negative 5 meters, right? And that would make this quantity, the slope, negative. I think you might remember from your old math classes, or whenever you took your math classes, that a line that slopes downward has a negative slope, and so these cars would have negative velocities if their slope was tipped downward. And so that's what this says in typeface. Delta x over delta t is less than 0. Delta x is x2 minus x1 is less than 0. And so the car is traveling in the negative x direction. So now here's where things get interesting. What can you say about a car if its position versus time graph is doing this? Right? It's curving upward. And so let me draw that on my slide here, on my whiteboard. So if I have a position versus time graph that looks like this, hopefully my camera will stay in focus, right? Here's my x and here's my t, right? Not very good. Try it again. Right? Now I can say, well, look, here's t1 and here's t2. Notice I can no longer really talk about the average velocity. I mean, I could, but since it's not a straight line, the car is doing something different here than it is here. But I can start thinking about what the concept of slope means. The sort of the slope right here is like this, right? The slope at this point, whereas the slope at this point, I didn't do that very good, maybe here, is like this, right? As the car is traveling along, you can see the slope is increasing, right? And so this is a car speeding up. Right? The slope is just whatever the car is doing at that instant. You might imagine that the car has headlights or something, and so the headlights would point along the line that's sort of tangent to the slope, and the slope is steadily increasing, and so the speed of the car is increasing. No longer do I have a straight line, I have a curve, and so this curve allows me to say that, oh, it's got a shallower slope here and a steeper slope here, and so the car is speeding up as it's traveling along. What is this car doing? Right? Hopefully you can see that the slope is steeper here than it is here. This is a car that's slowing down. Right? By the way, the slope is always positive in these, right? Because if I took an instantaneous slope, it would be sloped like this, right? Which is a positive slope, it's tipped upwards, and so these cars are traveling in the positive direction. Similarly, this is a car that starts out with a steep negative slope and a less steep negative slope later on. And so this is a car that's traveling in the negative direction and slowing down. You might want to spend a little time looking at those. You can even draw little pictures, hopefully, and give you a better picture of that. This is a car that's traveling in the negative direction and speeding up. And here are a few questions that you can see if you can answer. What do the variables x, t, and v each represent, right? What do those specific ones, x1, x2, v1, v2, t1, and t2 represent? In a position versus time graph, what physical quantity is represented in the slope? And then there are a few examples you could work out.